afternoon. So it's my great pleasure to introduce PManz from the University of Greifswald in Germany. And the title of his talk is How the Boundary Layer Determines the Operational Space of a Tokamak. The floor is all yours.
Okay, thank you, Lothar. Yeah, so I want to derive, in fact, the operational space in the tokamak, and I just want to do it only from the boundary, which in this case is a matrix. Yeah. And therefore it fits very good to the topic with turbulent boundary layers, of meant a different way. So why I do this? So there's a current challenge of power exhaust in the future fusion devices, at least in tokamak configuration with standard diverter as planned in ITER or in Spark. So this was also introduced by Nico already. The main point is that you generate the power, and everything which comes in also goes out, and it usually goes out at the outer midplane due to the ballooning instability, and then the power flux is moving here downstream the field lines to the target. And this depends on several quantities, and one of them is, of course, how much power you cross with the separatrix, but then this lambda q, which is the broadening impact of this heat flux in this channel. Other things are, in fact, your major radius, because here on the center, then you have here the radius. So if you have a larger machine, then it distributes longer. Heat line expansion is important, or the tilting angle, but to a huge degree, it depends on this lambda q scaling. And it's found out that lambda q scales with a colloidal magnetic field strength, and it decreases, unfortunately, which is not so good. And here you see that you are on already a few millimeter for CMOD values, and it goes under a millimeter for ITER, which then means if you do the power calculation for ITER-like scenarios, you will get a power flux on the target, which is for 40 to 80 megawatts per square meter, and this is much above, in fact, any material limits what you can set. It's even, in fact, somehow similar what you would have on the sun surface. And so you would not expect that you can build a reactor material on the sun. So it's much too much, and then there had to be something. So power load can be then reduced through radiative cooling. This was also a little bit introduced later. So you introduce some special impurities, neon, argon, and so on. And everyone has his cell phones temperature range where they can radiate. And this is usually above some tens of electrons. And so you can, if you manage to get the impurities in some parts in the diverter and it does not leak into the machine, then you may radiate the power away. Of course, if you need more power to radiate, you need more impurities. Yeah? And so it depends a lot then again on the power. So any kind of radiation scenario, also later if you cool down, you can get recombination and detection effect. This all depends on density, because they are collisionless processes, and they depend on density squared. The upstream density and the target density, they are connected. So if you have a higher upstream density, then you have a lower downstream density too. And so it's much easier to detach. And if you have a higher density, you radiate more efficient. So that's and you would need less impurities. And if you would need less impurities, this is good, because then if there are less impurities, they can also not go to the core. The lambda q is also important because it makes how much it is redistributed, and then it scales against with power. So less power is of course also good, but if you have less power, again, everything which comes in comes out, means you would have lower fusion efficiency also. Yeah, you may not want to do less power. On this scale, it might be also good. So the main questions are, in fact, what separatrix density can be accessed, so we can plan up any density we want. So we want to get as high as possible. But we have seen today in the morning, there's a density limit, and there may be disruptions, and one disruption in ITER would destroy the machine. So you may want to avoid this. But you also need then these kinds of density limits. And then there is a point that this scaling law, which I showed before, is coming from infrared data, which is only working out precisely if there's no radiation on the way. So this is all done at low densities and scaling also low densities. So we ask ourselves, how does this power width in fact change if we go for higher density? How does this compare to this ETPA scaling? And can edge mode condition be sustained? So we would operate in ether still usually as in high. We cannot make a negative triangularity plasma out of ether anymore. I guess it's too late, yeah. Yeah, so it's not into the discussion, yeah.
You could just junk it and start.
Yeah, how can edge mode conditions be sustained at high density that you detach at the same time and then we are fine? So where's the user project? Yeah.
Excuse me. In your picture, there is a CX. In your formula, there is a CZ.
It's charge exchange. I did not get the point. So there are, of course, ionization processes, but there's also charge exchange. Okay. Additionally to this unusual friction.
CZ is more general. There's more process.
So I did not. CX is for, there are also charge exchange collision processes at these temperatures. And CZ should be the concentration of the impurity of, yeah. So there are different things on them. Yeah, so I did not think about this. So now that it might be. Okay, yeah, so this is charge exchange. Initial friction, this is important for the detachment process because it asks, because you need power removal and momentum removal, and for the momentum removal, you need also the, but it's in fact not part of the problem. But sometimes I want to use the slides for the okay, so you cannot dial up arbitrary density temperatures as you want to, and you also do not get the gradients as you want to. Instead, there are constraints, and they are set by different things. So there's this density limit, for example, we have seen today, which here in this plot works pretty nicely at least. Then the gradients are restricted mainly in the pedestal due to image instabilities. This is feeling ballooning modes if you want to here large scale ideal ballooning modes, external modes. Here's shown now the ideal ballooning mode, which is in fact on then the confinement is also one of these kinds of constraints because you want to maintain high confinement mode. And the power threshold for the transition from low confinement to high confinement, this also depends on density. So there's a minimum and you want usually to be around the minimum, otherwise you need too much power and this costs too much. Yeah. And so the extrapolation to the machine, in particular for the Elmo density limit and for the LH transition, relies only on empirical scaling laws up to now. The MHD ballooning limit is, of course, understood very well. So this is not empirical. But you need to consider them as all at the same time. So I first done now with my first question. I want to address how does the power width change with higher densities beyond this ETPA scaling? And the question was there, does turbulence and widen the power if the density increases and the collisionality increases? And what would be a good parameter to quantify the strength of the turbulence? And in fact, this is why I'm in this project, because I was asked by Thomas, in fact, exactly this question. So what could be used as a parameters? So I make a short introduction to the main types of instability. So the interchange instability, which is mainly occurring here. I make it a little bit larger that you can see it on the outboard side in the bed curvature region. So here is the curvature. And the curvature, that's for the curvature drift, the charge separation. So from the region where you have a high pressure, the ions move upwards, the electrons move downwards, and there's electric field. Eco-speed is pushing this outwards. On the other side, it's pushing this inwards, where you have the negative perturbation. So it's unstable and it would grow. So this is in fact the instability which usually does most of the transport. And on the other side, on the high field side, is the stabilizing. So we do not have a lot of turbulence there. The other instability I talk a lot about today is the drift wave. The drift wave is working if you have a pressure perturbation in the gradient, and then along the gradient you have a finite wave. So there's something changing along the field line, and then this change, this is then seen by the electrons. So here you have a high pressure perturbation, you have a low pressure perturbation. The electrons will see this, so they go for the low pressure, move on the other side. A little bit more sensitive than I want. From the high pressure perturbation, then move on the other side. Okay, I pointed out on the other. Yeah. So here you have high pressure perturbation. Here, so electrons are moving here, then here the electrons go here, the lead and behind the electric field is introducing speed velocities, and so this will move downwards, and so it's then moving. So you have a propagation, therefore it's called the drift wave. Smooth electron diamagnetic attraction. Usually you will see in textbooks, density and radial velocity fluctuations are in phase. For the interchange, there's high transport, vanishing parallel wave numbers, and there's no phase velocity. You have drift wave, density and potential is in phase, no transport, finite wave number. And you would say, okay, have I those or those? Yeah, but in reality, of course, both are at the same time. So you have always curvature, there's always a charge separation. And if you go on the low fields, from low field side to high field side, you have a variation. So the drift waves will be always active. And so if you start to do this charge separation, then the electrons will see this, they will react on this and compensate for this effect. So it's less growth. And therefore, the drift wave is stabilizing on interchanges. It's a good thing to have drift waves. It's not bad. Yeah. Otherwise, you have interchanges. It's bad. Yeah. And this is then called diamagnetic stabilization. And this is when this, in fact, somehow starts because PManz was asked to use this parameter here, which is in this Roger Drake-Zeiler picture, and it's called the diamagnetic parameter because it describes how interchange instabilities are stabilized by drift waves, and they call this diamagnetic stabilization because, in fact, this diamagnetic parameter here is looking a little bit difficult. Depends on the ratio of the length of the drift waves to the time of the drift waves and the time of the resistive ballooning mode and the length of the resistive ballooning mode. So you have here then the growth of the resistive ballooning mode in time, how it grows, the length, the wavelength. And then because of this drift activity, it would drift away when it grows, and then it gets mixed. Yeah, and this diamagnetic propagation is stabilizing. And we should use this parameter to quantify how strong the turbulence is. So this was in fact the task. The main problem is that it depends 2 times on the gradient. And if we scale our gradient, which is a quantity where we have to know the gradient too, it does not make any sense because then we just go into circles and we do not have any predictive power. So we are asking if we get the same parameter without any gradient dependence. So now I do this with a equation system, which are now introduced in a similar way if I introduce now the instabilities, which is called the drift-Alfvén model from Paul Scott, which I have worked along with. It looks very similar. We will see the different terms when I explain the instabilities again. So we have a curvature operator, which does the charge separation, appearing here in the vorticity equation, which does the charge separation. And then we have an E equals B velocity in presence of a pressure gradient on the other side. Then you make the time derivatives on both of that. You linearize those. You have 2 times a growth rate and something on the other side. You get the growth rate, which is then depending on something square. So you take the square root. And here in the system, the interchange instability is just the square root of omega b, which is part of the curvature operator, in fact. Yeah, so good, I have it on those. So if you recalculate in this omega b and the units in the Steiff unit, you would see that it's the same. So it's here, in fact, very, very easy, in fact. You can have then a resistive ballooning mode. If you take this growth rate already calculated and take this as a time derivative here, and then to get in, so this growth rate does not have any scale. So usually you want to get the growth rate depending on the scale and maximum growth rate and so on, and then you would get the scale, but this does not depend on scale. So to get the scale, in fact, you make it now closer to resistivity. So you want to have this resistivity. Resistivity does not couple to the potential. So you take the potential, there's a current, and you take both of those. When you solve for this, then you get the resistive ballooning mode wave number. I will use it later again, but this is then the same as the other one in Roger Drake-Zeiler's Braginski model. It's equally the same, just written in a different way. Yeah, in these units. So it's also looking difficult in the other side. So if you want to have drift waves, I do not do the derivation of the all of those, then you would have to take the density gradient and the reflection in the density gradient into account. So these are parts of the drift wave. Then you need the parallel current response, which is very fundamental for the drift wave. You have to close this with the vorticity. And then if you want to make it unstable, because it would otherwise not be, then you take this resistivity here into account. And if you take the time derivative also for the potential, then you have Hasegawa-Ratta current. So it's a subset, for example, of this. If you want to go electromagnetic and make alpha waves, you have to take into account induction. You balance this as a parallel derivative of the potential. Take this to the, so only the black ones would be then the alpha wave. And then you get the dispersion relation square. So the omega is 1 over square root omega b. And it's just the dispersion relation of an alpha wave. So they are very handy, in fact, because you have just one sign always in this equation system. It's very, very nice. Yeah. So if you want to do diamagnetic stabilization, you take the interchange part, which does the charge separation. You balance this by the parallel response of the drift wave. And then you go, you solve for the potential equal to the pressure, which gives you some kind of Boltzmann relation. This is different by an I, and this is this I delta model we have also seen before in this morning, yeah. And this gives the cross phase, and this is the cross phase. In fact, you can identify this value as a cross phase, and the cross phase gives you the growth rate. And then you see this parameter, and we define now this parameter, which is the collisionality times omega b, which is the curvature radius, as our control parameter for the turbulence. And this does not depend on the pressure gradient, even so everything I think on the pressure gradient. And it will determine, in fact, how strong the turbulence is, because if the parameter is low, we have an adiabatic response, potential and density are in phase, we have no transport. If this value is high, we get interchange instabilities, this is high. So then we can do the data analysis of the plots, and then we see for our RSLEX database, it's a density gradient, normalized to rho s pol, temperature gradient, normalized to rho s pol. So rho s pol is the limit of what you observe in, if you have no density. In fact, this Goldstein's heuristic scaling is the ITPA scaling. This is normalized to this value, or it's somehow if you want the drift plane displacement, yeah. Therefore, we use this for normalization. Then you see that this is roughly increasing with a factor alpha t to the square, also for pressure. So you can see that gradient lengths are increased widening with alpha t, and also kind of strongly, but it's still just for the temperature, which is then the most important part, the factor 3, and so you do not get so much. So if you get high density, then it widens the factor 3. That's maximum what you can expect. So we have answered the first problem, and then we were very happy. But during this time, then we had to see, okay, we had this parameter, and then okay, I did not know that I wanted to show this. So if you have then drift alpha in turbulence, then you can calculate from this alpha d parameter again, or you can also do it with alpha t. You can expect then in scaling what you want to see for drift wave interchange expectations. You would expect that your pressure gradient would scale with alpha t to the power 0.285. And we did a regression for L modes. In fact, and for L modes, we would see that the database scales with alpha t to the power 0.98 and 298, which is very close to it. So the scaling in L modes is like expected for this drift interchange instabilities. But these I did not say it's for H mode, because you want to be in this high confinement regime, and there you get a different scaling now. And I cannot explain why this is happening. I have no idea. So if someone has an idea how to get to the scaling, that would be very, very important for us. Yeah. So I do not know why. For L mode, I guess that's in line with the expectations, but for high confinement mode, I don't know. So I want to go for the boundary layer. So I first go for the
Every time them two have an interchange or don't together, but you discussed how you get this entangled sum in your model. If you were to just put drift weight, especially in that field,
Just drift wave.
Because the field in
I can do the math. I did not do it. Yeah.
that would be helpful. Don't the Weathergeber Academy might very often use very close to separatrix in the edge. That would be an interesting sanity check. This has study.
I think curvature is the main drive for the instabilities. I guess it's more important, even. But I can check. Yeah, so we can. It's in fact, I guess for one machine it does not matter so much. 1 over R you would not matter. So I guess it's not as distinguishable because it's mainly resistivity or collisionality scaling because we do not change the curvature. So it's can be only found in a multi-machine comparison. How strong the curvature. We'll see another machine. So I go next for the density limit here to talk today. So we get already to this alpha D parameter, and this was in this Roger-Drake-Tyler picture. And on the Roger-Drake-Tyler picture, there's in fact they wanted to do the same. So you had in fact all these instabilities in. There's an ideal MHD ballooning limit. On the upper boundary, there is a density limit, which is explained by explosive resistive ballooning modes, and there's a high confinement mode. And in fact, the alpha D parameter is between 0 and 1 here in this picture. So everything is resistive ballooning. You go to drift wave, you move out of the picture. But if you go up in alpha MHD and you are at low alpha D parameter, so in the interchange regime, then you get a density limit and everything explodes. And if you are more or less drift wave-like and you get up with your plasma beta, you get electromagnetic, then you get in high confinement mode. This was the idea of this. Yeah. And then I might think, okay, just for fun, how does this now look with our database, which we use then for this? And we plot just alpha MHD against alpha D. And you see this parabola and you see the other values. So the numbers are not fitting because we are all above 1 and this is all below 1. And we have a higher alpha MHD than 1, for example, but the shape is fine. Yeah, all disruptions, which are labeled here by red stars, or H mode density limits labeled by the blue stars, they align on this parabola. And so I guess it would be fine to give it a chance. So how to get to this argumentation from Roger-Drake-Tyler? So we had to include how we get in these electromagnetic effects. So you want to make now the resistive ballooning mode electromagnetic. How to do this? So this is decided the turbulent regime in Ohm's law. So there are all of the parameters: collisionality, plasma beta, electron ion ratio. There's decided what kind of turbulence we have. So if you want to say, okay, we are electromagnetic or not, then induction must be larger than the electron inertia, otherwise you cannot get electromagnetic fluctuations. So we just balance both of these terms, then both have a time derivative, we can cancel those. Then we take into account Ohm's law, make a Fourier transformation of that, and we put this in, then we can get rid of the current, and then we see it depends on the wave number. So there's a ratio of plasma beta to the ion to electron mass ratio, electron to ion mass ratio. Okay, and if the wave number is smaller than this value, you are electromagnetic, and if it's larger, you're electrostatic. So always, if you go small, you're always electrostatic, and if you go large, you are always electromagnetic. Even if you have a really low plasma beta, you have large MHD instabilities. If they are large, they are MHD. If they are small, they get electrostatic. So this is a wave number. And so we define now this wave number as a transition from electromagnetic to electrostatic. And then we compare the electromagnetic wave number to the resistive ballooning mode wave number as a transition that the resistive ballooning mode would get electromagnetic. So then we plot the electromagnetic wave number against the resistive ballooning mode. And then you see at the point where the resistive ballooning mode gets electromagnetic, so the wave numbers are the same, then you get a disruption. And for all L modes, this is working, and it's pretty fine. All disruptive phases fulfill this criterion. If they are in high confinement mode, it's not. So it's just for L modes. the criterion does not count. And why does it not count? Because the turbulence is suppressed and we do not have resistive ballooning modes in high confinement mode. So it does not matter what I calculate, it does not matter, yeah, because it's not there. We can make a closement and now take this criterion, introduce Greenwald density, and then we get that this is in fact the Greenwald density with in fact no like dependencies because the other things which are there do not vary. And so this is a classical Greenwald limit to first degree. It does not change with power. So we might say the classical Greenwald limit is 1, but it's the best approach for classical Greenwald limit. So if we have that, then one might think, okay, then we maybe also can do MHD. So we go for the critical gradient. So to think now how to get a critical gradient, one thing is that we might now look for a transition from resistivity to induction and balance both of these terms. And then this wave number will give me a transition from ideal to resistive. So it's larger or smaller than this. In one case, it's resistive. In the other case, it's ideal. And then we had to derive the ideal ballooning mode from that. To do this, we take the interchange part again, because it's ballooning in both, and then we compensate this against the shear alphane wave. We take both of these into account. If we solve for this, we get a growth rate depending on gradient and the stabilizing term. We set the Dive equation right and become identical alpha MHD must be larger than the parallel wave number, which is in Dive usually 1, because it's normalized to 1. And this is fine for a textbook MHD thing, but it's not for reality. So we identify next that we set always our parallel wave number to the critical alpha MHD we get from the code. In fact, we can get an MHD code calculating critical alpha MHD, and then we approximate always our parallel wave number by this value. And then we are in agreement with the ideal ballooning mode. If we do so, we make a transition from the resistive ballooning mode to the ideal wave number. Then we get from a resistive ballooning mode to an ideal ballooning mode. And it's a transition we would expect that we get an ideal ballooning mode as an upper boundary. And we see in high confinement mode, no of the modes can cross this line, and it's an upper boundary from the data set. And it's analytically identical to the textbook alpha MHD is larger to critical. So there's nothing to say about this. We use alpha critical not from the MHD code, but from another formula here, which gives them the triangularity and the ellipticity, because we have a huge database and do not want to calculate all of this. But this works before, and it's completely consistent with Goldstein's approach for edge mode density limit values from the 2015 paper. And it's consistent with the data set then from Huber, from Jet, from 2015, 17, 2024, with I 2018, and then for Sunny from 2020. So this is pretty much, I guess, but we also know ideal MHD is working, so yeah, but it's working here too. Okay, then we go for confinement. It's maybe a little bit the most difficult part. So how to solve this? So we have the Dive equation, and we see this now as a kind of energy flow between different fields in the Dive turbulence. We start with something which comes from the gradient, and it's absorbed by the sonal flow, and it can go over different routes. So the turbulence or the gradient may be these trees, and then they are fed by the mouses and the deers, and then they go up to the snake and the eagles, and you do not know what it's doing. And then you can make a lot of Mimel cycles. This is the easiest case because I only take the equation system which I now use. So I can expand if you want with microtheory modes and kinetic ballooning modes, and then it goes even more crazy. And we can go from the sonal flow to the GAM to the global alphane waves, and then we can cross the circles like we want to. We can make it really, really complicated, but we keep it now as simple as that. So we start now how to kill the turbulence. So the turbulence will decay if the energy transfer to the flow exceeds the drive at the beginning. So we had done this, in fact, when I was working in UCSD with Pat also. And we did this also with loads of, in fact, on D3D. So this is the criteria. The energy transfer into the flow must be larger than the growth rate. So these are these two. And the energy is this production term, and the shear by the Reynolds stress. So these are those. And the energetic drive is by the pressure gradient of electrons and ions. They are a little bit different. So now looking for the drift drive interchange competition at the beginning, we have two kinds of cases. So we get charge separation by curvature or by the parallel gradient. And if we go by the parallel gradient, the energy goes to the magnetic energy and then later to the equals B, or we go with the curvature directly from pressure to ion drift energy. And deciding which one is stronger is decided here in the dissipation. So if there's a lot of dissipation, then this is drained, this value is low, and then because this depends here on this value, it's not going much then in this direction, and you go. If the resistivity is low, then this value is high, everything will go here, and then here. So this is then controlling, the dissipation is controlling which direction the energy will go. This is now important because alpha T is now controlling the way to go to the energy. So we have our control parameter alpha T from before. It controls the growth rate of the electron bunch, but not of the ions because they do not participate in the parallel response of the electrons. And you cannot stabilize ITG modes with drift waves. So we take an ideal interchange instability for them. Then we have a growth rate. We take the flow. Now the background here, we assume that it's ion diamagnetic neoclassical flow because we have seen this in Aztecs. Put this in. Then we have an efficiency of the coupling of the adiabaticity, how strong how effective, in fact, the zonal flow coupling is. This is also something which was on the last talk. Put this everything here in, and then we have our shear criterion, but depends still on two characteristic lengths. And for the parallel lengths, we now use our alpha critical to be consistent with the previous data set. And for the perpendicular wave number, we do not take the resistive ballooning mode because we tested it and did not work. Instead, we used then the KEM and it works. The explanation is the following. So you kill all your electrostatic turbulence, but you still have a lot of turbulence left. And this is electromagnetic. So you have kinetic ballooning modes, microtearing modes, and they are still there. They do fluctuations. You do not kill all of the turbulence. You just kill the electrostatic part. So we kill up to the electrostatics. We let the electromagnetic survive. And then we end up to this formula, and that's it. So it has a stabilization from the zonal flow via the Reynolds stress. This is this term on the stabilization side. You have an efficiency of the zonal flow coupling depending on the adiabaticity. The growth rate is reduced by the diamagnetic stabilization. And we have, because of the ITG part, a very important part of the ion heat flux, which was reported on Aztecs. And so we would have a formula which might work. We plot them together and separating L modes in green. So here is shown the destabilizing part on this side is shown here. The stabilizing part on this side is shown here. So the stabilizing part is here, destabilizing here. It's a one-to-one crossing point, in fact. And all L modes are above the dividing line. Really nice. So they're separated really strongly here. And all of the edge modes are on the stabilizing side. And that's it. So then I'm done. So I have the L mode density limit in this wave number space, value ballooning mode and the LH transition. And all depends on density and temperature. I know before because I can map them back. And then I can map them in the temperature density diagram because it's more easy to understand how this is working. So I map the LH transition line, which is higher for lower densities, and for high densities it's also then getting up. I have my L mode density limit and I would cross it, but I say, okay, it's not working for high confinement mode. So I stop always if I cross the blue line. And here I have my ideal ballooning mode. I can compare the data set and it's working fine. So this is the aim. So we have derived the green by density limits, ideal ballooning limit in the LH transition. Just for density and temperature values, we need the scaling law still. But one important point so is that this is then plotted from measurements, it's Thomson data. So the first plot is from 123 discharges, and in total 1,884 points. These are all points we have, all points. We did not do any exclusive. So we just, of course, we have no impurities then, so we only use data after boroughinization. But yeah, that's it. So the second plot is 2 years later. It's including 282 discharges, 3,700 28 data points without any exceptions. This is several years and campaigns. And the agreement is exceptional there. So 1 point for the Thomson scattering data, we do not calculate the temperature directly. So we calculate the power crossing the separatrix and using the Spitzer harm condition, which also Nico introducing on his fourth slide. So we get the temperature value, and then we set the separatrix position to this temperature and takes them from the Thomson scattering data, the density there. But we compare the differences to the equilibrium reconstruction, and it's usually only a few millimeters. Yeah, and the best is these boundary layers. If you now this separatrix operational space allows now to monitor the confinement modes, L or H mode. But the closeness to the disruption, I come later to this. But you also see with the separatrix density, you have also the power fall of length because you have the scaling laws depending on alpha t, and you have iso alpha t line, so you can see how much the diverter is broadening. So you have all important quantities for the access to detachment on the same page. So you know how much density I can get if I can detach or if I cannot detach, if I'm close to a disruption later. And this is temperature, which directly is the power. I also know the required heating power. And there are scaling laws for density and puffing ratio. And so I can now with puffing and power to get to every of this point. And this was also the reason why we could populate the high density, high temperature range from these campaigns before to the campaign last, because the operators now how to choose puffing and heating power to get to these points directly. It's working real time because it's just the formula you want to have. So it's really, really nice. So you may ask, okay, how this is working now for different current and magnetic fields. So we do not do a lot of these discharges. You can see the diagrams are moving with changing the magnetic field or the current. So if you increase the current, so this line is moving up, LH transition is going down. Of course, the density limit is also going on to higher densities if you increase the plasma current, but you cannot see if this is working or not because we do not have any data there. So of course, the diagrams are doing the job as you expect, but yeah, there's no data. If you decrease the magnetic field, we decrease the L to H power threshold. And here, these points are usually disruptive. And here they're in high confinement mode, for example, as predicted by the model. So it's working as expected with the database. It also works with Alcator C mode. Here's the data from Alcator C mode now. So comparing the wave number conditions for the density limit, ideal ballooning mode, and the L to S transition, you see it's all separating this in a good way. And in Alcator C mode, you can also plot now the separatrix operational space, and it's working for the database too. The cool thing, yeah, so here's the density limit, the ideal ballooning limit, and it's covering this space. And these are far different parameters, so with different major radius, minor radius, and same plasma current, but very different magnetic fields. And it's working. So also for different machines, so it seems to be pretty nice. So
30 minutes, 15 minutes.
15 minutes, yeah? Okay. Okay, then I do this now. Yeah. So this is now for the older guys. And on this Roger Drexler stuff. So the Roger Drexler stuff had some success, and then there was a counterexample, in fact, from D3D, which is I want to show here, and it's pellets. So what they do is, in fact, that they injected pellets in D3D, and sometimes you can induce an LH transition if you introduce the pellets. And so here you see this parameter. So they had. So here's the space, how they calculated it, and here you are before the pellet, and you inject the pellet here, and this is what will happen in space. And then after the LH transition, you move a little bit here up. And it's a little bit strange in this kind of coordinates because you move on the other side. So you increase the density, so you reduce alpha D because it's on the other side, it's the resistivity. So with increasing density, you move on the other side. And how can you ever with increasing the density, go in high confinement mode in this model. So it does not really make sense. Yeah. So this was using as a counterproof. In fact, this kind of model did not work, and we were very close to it. And so sometimes people are asking, how is it with pellets? Does it work with pellets? Yeah. So first I want to show the space base. So I plot now our lines in alpha MHD, alpha D lines, so these are not the predictive lines of Roger Drake-Zeiler. These are our lines in their coordinate system. And it would be more like the downer part. So we would here get a straight line, and then here is a little region, and we have really low values, and it's more or less a straight line. So I plot them logarithmic, that you can see how the separation is. And these are our lines, not there, but you can see that in principle the shape is still very, very similar in this way. So you must also say that they did just computer simulations, and they keep always the gradients the same. So in this figure, the gradient is always the same. So there's the same gradient in L modes and in H modes. So the alpha MHD is just the plasma beta, and alpha D is just the resistivity in their code. Yeah, and it's more complicated because alpha D and alpha MHD both depend on gradients, which both depends on density and temperature. And so it's very complicated, in fact, to understand what's happening because it's not so easy. So we do it now pellets, shoot them in, and look if we can introduce an LH transition. So first here it did not work at the beginning. So these lines are then the pellets. They make a blip in ECRH. So because of the densities, and you can see the pellets there. It did not to lead to something, but then here's the second one that increases here the density strongly, and you get the strong increase in alpha and WMHD. So you get an L2H transition, and we can now look how this looks like. And what's happening, in fact, is that you still do a small jump, and the jump is, in fact, an alpha MHD is really low, but you would not understand why you get to this jump also. But in the density temperature diagram, now, in our case, you can see what's happening. So you increase the density. And if you increase the density, the L2H transition power just goes down. This is known because you're on the low field part of this. And they did this upper single low density. And so, of course, in the low density regime, and the density increase triggers an LH transition just because your LH transition power threshold goes down. And this is then the reason why you get to it's very, very easy, in fact, to understand if you do this, but you cannot understand this in the alpha MHD diagram because it's just too abstract, yeah, to understand how the LH power threshold is changing in alpha MHD, alpha D. Just short, so we can ask, okay, how is it in favorable and unfavorable configuration? Can you explain this? So we then extended, in fact, our shear suppression criteria by taking the magnetic shear into account. This is work by Nicolas Fedorchak, in fact. So you thought then that you have this mode starting here on the outboard side, and then just by magnetic shear, these are deformed, and this deformation you can also see like in stress, and then you can make the Reynolds stress plus the modification by the magnetic shear. So we see also in the data set that our production values, if you just plot them against the destabilizing parts, in our favorable configurations, they have this 1-to-1 line, but in unfavorable configurations, they are also separated, but they are separated by 2.5. So we just had to explain 2.5. Then we did acrylic simulation to fit both of these constances for some cases, and then you can see that the contribution to the Reynolds stress is always 70%, and this one is around 30, one third. And then you can put them together. And in unfavorable configuration, has a magnetic field or upper single line. You put them on different signs, and then you can make the configuration, and then you can see that you get, in fact, this factor 2.5. In a nicer plot, this is done now by Alcator CMOD. So you introduce then this prefactor here. And then you can see how the L2H power threshold goes up. And then we could take this in effect into account. So this is a little bit fitted. You may now ask, okay, we can now, if this before works, we can normalize the temperature to the temperature at the L to H transition, and then the entire database collapses, in fact. So you can plot then the normalized electron temperature to a normalized electron density, and the entire ASICS database collapses to a uniform picture on an L to H transition. And you can calculate this then for Alcator CMOS and Spark. And if you normalize to the minimum temperature and the minimum density of the LH transition, we have a unified picture of all of the soccer mats. And so it seems that it can be used in a very general way. You can calculate then from the scaling laws the minimum density at the LH transition, and this is consistent with the Rüther-Schmidt-Meyer scaling for ASIC, ASCII, and CMOD. So we can recover these basic scaling laws of the L to H transition in a general way for different machines and powers. And that's what this is. I also have not shown. I wanted to go to this one too. That's not published, so I can plot the electron temperature minus the critical temperature of the LH transition divided by this critical temperature. Together we use temperature. And if I plot the mean of the plasma stored energy, also the complete machine ASTEX collapses to one line, which is quite of super interesting. And you can see gradient scaling relationships between these points that you get some critical behavior for low densities where you have an L to H transition, but not at high densities because there is no back transition. And you do also not see bifurcations at high density in the experiment. So it seems that it can be used, in fact, as a kind of order parameter. And you can calculate this all from the database analytically without any experiments now or computer simulations. And this is now the last one. So we can also put math models in. So we have a math model, for example, from Schrot here for the X-point radiator. When the math gets unstable, we call it math. And if the math gets stable, we call it 6-point radiator. Maybe a little bit different. It does that only depend on temperature. And then you can plot this here on the line and all fits through all of the disruptions. So this would be our disruptive line. And you could also put this into this operation space. It does not depend if this is L or H mode. And there's some gap. And you can see the edge, the modes which go back from high confinement mode and they survive. They're around this gap. So I guess this line is determined if you had a hard or soft limit out of the high confinement mode. And very important is this because at high densities, you may likely always have a hard limit and then it gets more dangerous. So it's working. You can say it's too simple and it's true. So there's a lot of things which should be important and I completely neglect. And I know, so I need trapping. I did not do anything on trapping. Some of the other parts are also much too easy, but yeah, it's working. So this has been developed on the basis of a dedicated database. So at the beginning, you might say, okay, we choose, in fact, that this is working only with this database, but now it's also working for Alcator CMOD, which we did not know before. And we had also much higher densities and so on. It's working, and all of the data sets for the next years were fitting. So it's it's working. This approach does not guarantee that we have an optimal solution. Also not complete, not self-consistent. Yeah, you can modify it and improve it. Yeah. And the only thing is, in fact, that we now get a really good agreement with the data set, which now justify that what we've done is somehow sensible, and you have our kind of model which you can use for design. And then, thank you.